Hey everybody, and welcome to McArdle Math Academy. In this video we're going to be talking about how to find center of mass using different integration techniques, and particularly we'll be looking at this first example here, which is a one-dimensional case with a rod that has varying density. So we want to find the center of mass, which should mean to you find the balance point of this rod on the x-axis, and it's pictured here. It's a 10-foot long rod, and it has mass density delta x equal to 10 plus x. So we know that as we move away from the origin, down the rod, each little segment over here is going to have a little bit more mass than the ones over here, based on this equation. Okay. So before we start anything, let's just make a couple notes. They give us delta x. Okay. Delta x is a mass density in this case, and by the units I can tell that this is mass over length because it's kilograms per foot. Okay, so what I can do with this equation is solve for mass, because I'm going to need this as we move forward. So if I solve this for mass, it's going to be delta x times length. Okay, and we're going to need this as we move forward. So now come back to our diagram here. If we're going to find the center of mass, it amounts to summing up the moments. So we saw in the discrete case, we sum up the moments, i.e. the position times the mass, and we divide by the total mass of the system. So we have to divide our rod into little slices. So here's my slice. My slice has a width of dx, and it's going to be located at a position of x. Okay. Now the very first step, once we get the slice with these types of problems, is to find the mass of my slice. Alright, so the mass of any arbitrary slice that you drew here, we're going to go back up and use what we just found, where mass is delta x times length. So the mass of our slice is going to be delta x, where x is the position of the slice, times the length of the slice, which is dx. So it's very simply delta x, which we have an equation for, that's 10 plus x dx. Okay, this is going to come in handy. Next step, we're going to find the total mass. We want the total mass of the whole rod. Well, we know that in order to find the total mass of the whole rod, we have to sum up the masses of all the slices. When the slices are infinitely small, that becomes an integral. We go from 0 to 10 for the positions of the slices, and then we just take the mass of each slice and throw it into this integral. So the integral of 10 plus x dx. All right, and I'm going to pause and I'm going to do this real fast. So I find that to be 150 kilograms. All right, and you can verify that yourself. So now that we have the total mass, we keep moving with our little procedure here. The third step is to take the equation that we know for the center of mass. X bar is what we call the center of mass, and we know we have an equation for that where the top, we're going to sum the moments, or have an integral of the moments. That's the position times the mass of a slice. And on the bottom we have the total mass, which we already found to be 150. Okay, so all we have to do now is put in the pieces that we have. So on the bottom we're going to have 150, and on the top we have the integral of x times the mass of a slice, which we found to be 10 plus x dx. And again, let's see if I can fit it in here, our bounds are from 0 to 10 on this integral. All right, so let's pull out the 1 over 150, and we're going to integrate. So what I'm going to do first is distribute this in here. So you get 10x plus x squared, and when I integrate I get 10x squared over 2 plus x to the third over 3, and we're going from 0 to 10. And when you go through the algebra there, you'll find that this is 50 over 9. And this is a center of mass. This is a position. So our position was given in feet. So it's going to be 50 over 9 feet. All right, and then what we do at the end of the problem is we just kind of make sure that this answer makes sense. So let me zoom out here so we can see the full picture, and we'll go back to the top here. We have a rod that's 10 feet long, And we just found that the center of mass is 50/9, which is, it works out to be about 5.6. So that means that the fulcrum point lies a little bit to the right of the center. That would be the balance point of the rod. And that makes sense looking back at the equation here, because as we get farther and farther out, the mass density is greater. So you would think that this would weigh a little bit more than this half, so the fulcrum would be on the side of the heavier part of the rod. All right. Hopefully this helps, guys. I'll see you next time.